So good morning, everybody. It's nice to see you. We'll go ahead and get started. So if you'd like to follow along with me in the book, we're covering material roughly equivalent to section 3.4. Like I mentioned online last time, like on the Google Classroom yesterday, this section is kind of like just a grab bag of a couple examples. It's really just reinforcing the fact that a derivative is a rate of change and how to interpret that. So it's really kind of learning examples and getting practice rather than a lot of new theory. So I think it's like a chance to help us practice some of the new techniques we learned last time in order to take derivatives. So I'd just like to go through, I guess what you might say, some guided examples with you, and I'll show you some of these formulas that are in the book that you may already be familiar with. But let's dive right in. So my first example, and rather than just being completely presentational, I'll give you a chance to work, and then you can compare your work to mine as we go along. So let's start with the area of a circle. So the area of a region bounded by a circle is, you might be familiar with the formula pi times radius squared, where r here is the radius of the circle. And so imagine in your mind not just one fixed circle, but the circle whose radius changes. So you might think of r like expanding, 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 and therefore the area would correspondingly get bigger and bigger and bigger as r gets larger. So area is really a function of the variable r. You take whatever circle of whatever radius, and out comes the area of that circle. And so therefore you can compute the rate of change of the area, like with respect to that radius. And so that's the first thing I'll ask you to do. So please compute the derivative of a with respect to r. I could have also used this other notation. This is Leibniz notation, I think people call it. But these mean the same thing. This would mean the derivative of a with respect to r. This is the derivative of a with respect to the variable r. So please calculate the derivative of this at r equals 2 and r equals 5. So calculate the instantaneous rate of change of the area of the circle at r equals 2 and r equals 5. I'll give you a minute to do that, and then I'll come back and we can discuss. So after giving you a moment, I'll I'll share my work. So here I want to use the power rule to calculate the derivative. So pi is a constant. So the derivative of the area with respect to r will be pi times the derivative of r squared. So that's going to give me 2 times pi times r. That's the general formula. And this might be kind of interesting to you because the derivative of the area, the instantaneous rate of change of the area, is actually equal to the circumference. This is the formula for the circumference. Circumference is the length, the sort of like the perimeter of the circle, if you like. And I always thought that was interesting, how when you take a derivative of area or volume, you would get the corresponding formula for length or surface area. You'll see that as we continue on in the course. But at r equals 2, you're just plugging in r equals 2, so you're getting 4 pi. That's the answer there. At r equals 5, you're plugging in 5 and getting 10 pi as your answer. And so like another way of writing this would be, just to practice that notation, it'd be dA dr, and you draw a vertical line and write r equals 2. So if you're on a test and I ask you for that, then the answer is 4 pi. You're finding that general formula first, derivative as a function, and then you're plugging in r equals 2. Similarly for this one, dA dr at r equals 5. And so the next question that I want to ask you, and this is the one where where young students are more likely to struggle with how to answer it, because I think when we're starting out, we're better at making calculations than we are at communicating explanations. So think about how you might try to communicate this. So what's going on? Part B, what I'm going to ask you is, can you explain geometrically why the derivative is bigger at r equals 5 than it is at r equals 2? So why is the instantaneous rate of change, why is a prime of r bigger at r equals 5? So if you can try to draw a picture to visualize that for yourself, I think that'll help a lot. So why is the instantaneous rate of change actually bigger when r equals 5? I'll give you a moment to think over that. So now that you've had some time to think, and you're welcome to keep thinking about it, but I'll try to explain it as well. So why is this bigger? Why is the instantaneous rate of change bigger at r equals 5? And in order to do this, we need to, I think we need to understand something about what that instantaneous rate of change is. So remember that this notation, like dAdr, the reason why it's good is it's kind of suggestive. So remember that what the definition of the derivative is it's this limit, if you like, as delta r is going to 0 of the rate of change of area over the rate of change of r. And like if you want to write, this is how a physicist might write and think, if you want to write it like more in a way that's more formulaic, then yeah, you can write down like a of r plus h minus a of r divided by h. So your h is like your change in r. And then you would take limit as h goes to 0, and that's two different ways of expressing the same thing. So this is more mathematically formal, and this is a little better at conveying the geometric idea of what's happening. Although as a student, this puts you in the danger zone a little bit, because you do want to be able to understand both interpretations. You want to be able to understand this expression equally well as that one. Okay, so what's going on? So let's try to put it in terms of a picture. So let's take some circle, and let's say this is 0, and here would be r equals 1, 2, 3, 4, 5. And let's draw this circle of radius 2. And I know I'm not going to be great at circle drawing, but bear with me. So 2, and then 3, 4, 5. So here's the circle at radius 5. And now let's investigate what's this delta A over delta R. So let's take a small change in R. And on the board, I'll just represent that as I'll represent delta R as being 1/2. So I'll go like half the distance, just so you can see it. But in general, you're thinking about a really small value. So when you have a change in R, you have R going from 2 to 2.5, right? So delta R in my picture is 0.5. And delta A is going to be the area of the circle that's inside the orange part minus the area of the circle of radius 2. So the change in area is going to be really the area of this cylindrical region. Like people call this like a washer. It'd be the area of that washer. So that's delta A. So delta A over delta R. So delta A is like the orange region. So delta A over delta R is going to be this area divided by 1/2. But if you look at R equals 5, and you still go out 1/2 with the same delta R, here's the region that you get. And this is still like R goes from 5 to 5.5. So it's the same value of R. It's the same value of R. But the thickness, but the area of the cylindrical region is definitely bigger, right? This area is definitely bigger than that area, even though I had the same value of delta R. So delta A over delta R is going to be definitely bigger for r equals 5 than it will be for r equals 2. I'll pause for any questions. And when you're talking about what's the derivative is the limit of delta A over delta R as delta R tends towards 0. So here's delta R equals half. Delta R equals a fourth, then this orange cylinder would be half of its thickness. Delta R goes to an eighth, then you'd just be going from here to here. So as delta R is tending towards 0, this orange circle is tending towards the white one, and therefore geometrically you can see, without even knowing the product rule or anything, geometrically you can see that delta A over delta R, as this delta R is tending towards 0, this limit tends towards the circumference of the circle at R equals 5. So you can see geometrically why this formula really makes sense, because dAdr is the limit of change in A over change in R. And the change in A is this cylindrical region whose area is basically something like, the area of this region is going to be area of the base circle times the thickness. So it's basically 2 pi r times delta r. It's going to be similar to that. And we're dividing by delta r. So you can see that that limit as delta r goes to 0, it's going to tend towards 2 pi r. So there's some, I hope, some geometric reasoning to go along with just the power rule. And that might also help you understand why, like more generally, the derivative of volume is going to be surface area. Derivative of an area formula, it's usually a perimeter. And it also tells you that as you go out further in the radius, even if you make the same change in r, like this is supposed to represent 1/2, that's supposed to represent 1/2. Like maybe I drew it like a little bit bigger, but you take the same change in r, but your change in area will be much bigger, just by virtue of the fact that you've gone farther out in the radius. So how could you write that? Yeah, why is delta r 1/2? I just chose this. I just chose this for the picture. Delta r is going to be any small number, and eventually you'll take the limit as delta r goes to 0. But I just chose to illustrate one particular delta r. Yeah. Any other questions? Okay, cool. So that's an example with like areas. There's another example from economics. You talk about like marginal cost. I won't belabor this too much, although I will tell you that the book kind of, the book is kind of inconsistent, because they're going to give you one definition for marginal cost in this section, and they'll give you a different one in another section. So what's going on? I'll just briefly mention this. So like if you take an economics class, you'll hear the economists talk about like the cost function. So this is like cost in today's dollars to produce to produce x units. And the domain of this function is really like, 1, 2, 3, 4, 5, 6. But at the scale at which companies produce things, millions of units or whatever, it's reasonable to approximate that discrete function like with a polynomial or something, or even some other smooth function. So anyway, you're working at a company and you'll compute some cost function, and then the marginal cost you'll define to be the derivative at that point, x. So this is called the marginal cost. And so where does this come from? Like what does it mean, and why does it mean this? What it's supposed to be is, roughly speaking, what you're supposed to interpret this as approximately this is the cost to increase production by 1 unit. I'm not going to lie to you. I don't care about economics that much, but but I do want to give you like a range of examples. So if you've got some cost function, like the marginal cost is supposed to be approximately the cost to increase production by 1 unit. So why does that make sense? Why does it make sense that this could be the derivative of the cost function? The reason is that if you again go back and write down definition of derivative, is like the limit of the cost to produce like x plus h minus the cost to produce x divided by h. So in calculus, you would think of taking a limit as h goes to 0. In practice, if x is like a big number and like 10 million or something like that, and you want to know like what's the marginal cost to produce like 10 million in 1 unit, like you're wanting to increase, or more likely you're wanting to increase production by 1,000 units. So what does it actually cost you to make that increase? Then in that world, h equals 1 is actually the smallest number you can get, because you can't produce like half a unit, right? So you wouldn't actually take a limit as h goes to 0. You would actually approximate this just by substituting in h equal to 1. So you would actually just sort of plug in c of x plus 1, like the cost to produce x plus 1 minus the cost to produce x, divided by 1. And this is actually your book definition of marginal cost. But I think the calculus authors are trying to define it this way to make it easier on you or something. I don't know, but later on they'll go ahead and define it that way. It's kind of weird, but this is the definition that like economists use. Like this is the definition of marginal cost. It's the derivative of your cost function. It's motivated by the fact that the derivative basically tells you approximately the cost to increase production by 1 unit. So any question on that? And so with that concept done, like we'll go through this example. And so usually, like these are fairly realistic, I guess. So usually your cost functions are polynomials. So let's go through this example. So company data suggests that when there are 50 or more passengers, the total dollar cost of a certain flight is approximately given by following formula. See, so this is like word problems. Approximately given by the following formula: 0.0005 times x cubed minus 0.38 x squared plus 120 times x, where x is the number of passengers. So input the number of passengers, output the total cost in dollars of running a flight with that many passengers. And this is going to be valid so long as you've got more than 50 people on the plane. So estimate the marginal cost. So like say 150 people are flying. So what is I'll say it the way the book says it. So estimate the marginal cost of adding one more passenger. So let me give you half a minute to think about this. The problem is not going to be taking the derivative. The problem is going to be reading this and understanding what calculation you need to make. So take a moment and think that through. Okay, so what's going on here? The reason why this, well, there could be a couple of reasons why this might be confusing, but like one reason is I think there are two ways to think about this. And you know, back in the days when like computers and calculators weren't ubiquitous, one way was definitely easier, but like nowadays it doesn't really matter. So like you might reasonably say like, what's the point of this? But the point is to introduce a concept and get used to it. So on one hand, the literal answer to this question, like how much does it cost to add one more passenger? Isn't that going to be the cost of flying 151 people minus the cost of flying 150 people? I worked this out on Desmos while I was letting you work too, and the answer that I got was 39.5955. So roughly, this is $39.60 to add another passenger. That is literally what it is, right? You're taking the cost to fly 151 minus the cost to fly 150. That's the cost to add another person. So you want your ticket price to be more than $39.60. In order to do the estimate, how can you do that? Like, you can also estimate this by just looking at C prime of 150. And so why is that true? That's true just because, like, as we've noted, since this was the limit as h goes to 0, and since our smallest unit for h is like h equals 1, then, like, if you were actually trying to approximate this, like, without actually taking the limit, then you would do cost of 150 plus 1 minus cost of 150 divided by 1, right? Which is just C151 minus C150. But you also have this nice function, and so you can approximate this just by taking the derivative and plugging in 150. So let's check that. So let's take the derivative. And so this is going to be like 0.0005 times 3 times x squared. So, like, what is that? Is it 0.0015 times x squared, and then minus 0.38, and it's 2 times x? So what's 38 times 2? It's like 74? Is this minus 0.74x plus 120? The way you do derivatives like this in your head is hide the constant. This is 3x squared, then multiply the 3 times the constant. Hide the constant, take the derivative, that's 2 times x, then multiply 2 times negative 0.38. Hide the constant, derivative of x is equal to 1, you're left with just 120. So there's your derivative function. You plug in 150 to that using a calculator. Hopefully you get a number that's a reasonable approximation to this. And I'll share my screen with you and show you. Yeah, the question is, what's the reason for dividing by 1? Because what I'm doing is number plus h minus number divided by h. And so if I were taking the limit as h goes to 0, I would get the derivative. But instead of taking that limit, I'm getting an approximation, right? So this should be like approximately equal to that. That's why I use this squiggly sign. But then, like in the model that we're using, in the mathematical model that we're using, the smallest choice for h that you can choose is h equals 1, because it's, x has to represent like a number of passengers. And that's the reason for choosing h equals 1, because it's the smallest value that you can actually plug in to your mathematical model. And so that's why the derivative, plug in 150, should give us approximately something similar to actually calculating 151 and then actually calculating 150 and taking the difference. The reason why using a derivative is nicer is because plugging in 151 is kind of a difficult operation. Plugging in 150 is kind of a difficult operation. Then you have to do the subtraction. Whereas taking the derivative and just plugging in 150, it's a little bit less processing time, and you actually do care about things like that when you scale up really large and you're doing lots and lots of calculations. Even with the fast computers of today, we do keep track of how long it takes to compute things. Take a computer science class on analysis of algorithms for more info on that stuff, if it tickles your fancy. So here's the calculation that I made to check my work. So I typed in, I called it f of x instead of c of x, but I typed in the thing. I typed in f prime of 150, and in order to get the computer to calculate it for me. And the answer that came back was $39.75, which is quite close to the actual answer of $39.60. So that's kind of a cool example of the theory telling us that something should be true, and then it actually does turn out that this difference can be reasonably approximated by the derivative at the point 150. So I like that. I think that's kind of cool. This example has multiple parts. Let's continue on. Oh, well, I guess we actually just kind of did them. Compare your estimate with the actual cost of adding a passenger. Yeah, I didn't read the instructions in advance, but went ahead and did the other things we're supposed to do. This would be the actual cost, the $39.60, and our estimate was C prime of 150 is equal to like 39.75. Just saw that from Desmos. You can check that by plugging in 150 for X. And finally, part C says, is it more expensive to add a passenger when X equals 150 or when X equals 200? I don't know that there's any way to do this without just actually making the estimate. So it says, is it more expensive to add a passenger when you're flying 150 or when you're flying 200? So is it more expensive to go up to 151 or is it more expensive to go up to 201? And I mean, let's just investigate this numerically. Let's just discover the answer. I mean, there's this general principle in business that things get cheaper as you scale up, but let's just see what happens. I think I'd like to do this on Desmos. So F prime of 150, so that's the rough estimate for the cost to scale up 150 people and then add one more passenger. But say that you already had 200. What would be the cost to go from 200 to 201? Like, what's our estimate for that? It's F prime. And our estimate for going from 200 customers to 201 customers is actually $28. So you have much higher profit margins on customers once the plane is sort of like getting full. And airlines are going to be charging more at the last minute anyway, so like their profit margins go way up in that instance. It's kind of interesting to think about that. Like, just the fact of being able to write a cost function down, you're now able to calculate all these things like marginal cost, like cost to add one more passenger if we're at this level, if we're at that level, just like automatically. And that can allow you to decide analytically what kind of deals you want to offer, when you want to offer them, so on and so forth. Of course, there's like this whole industry around advertising and pricing that's more complex than just Calculus 1, but this is a first step towards like thinking in that direction. And of course, there's a whole political thing about like whether we should be doing those kind of things or like whether it is good or bad to be collecting data on people and then using that data. And I have opinions on that. You might have opinions on that too, but like for this class, I'm trying to focus on showing the mathematics. Okay. See if we can sneak in one more example. I mean, the other thing is this idea of motion under the influence of gravity, and this is the motivation for studying calculus in the first place. And there's this little blurb in the book about linear motion, and so linear motion is just motion in a straight line, and I'll give you some setup. Like if you're talking about motion in a straight line, you often use function s for position and t for time. In international standard units, the position would be in meters and time would be measured in seconds. There's many kinds of linear motion, right? Like you could think of a car driving forward with time on a straight road. And then you would have the position of the vehicle with respect to time. What's another example? Like one of the classic ones that you're introduced to in physics early on is the mass spring system. So this is like the simple harmonic motion where you've got a weight or a mass tied to a spring. It's at rest, so you pull it down from rest and then let it go, and it'll like wiggle around. And there's an equation you can derive. Take a differential equations course. To figure out about that and even more. But since it would be motion in a straight line, you could describe it by some function you might call s of t. The other thing that we'll probably talk about in this class, like, is if you take something, like you take some mass and you hold it up. You hold it up high, like 100 meters or something, or think about the apple falling from the tree, and then you just drop this and let it fall under the influence of gravity. Its position will change in time as it falls to the ground. Represent that with this function s of t. And so we will then look at what you might call the velocity, v of t. That's the instantaneous rate of change of the position. That's your speed. You're driving your car, your position is where you are, your velocity is your speed. This is, like in high school physics, you usually use average rate of change for velocity. In higher mathematics, we use instantaneous rate of change when we're talking about velocity as much as we possibly can. So this is really the derivative of the position, because it's change in position over change in time, and that's your formula for velocity. Then you're taking that limit as delta t goes to 0, giving you instantaneous rate of change. And then the third fundamental quantity or fact is going to be, you also look at, it sounds kind of silly to describe it, but you also look at the rate of change of velocity. So you don't just look at how fast you're going, you look at how fast your speed is increasing or decreasing. And in fact, that has a name too. The instantaneous rate of change of your velocity. So this is going to be the second derivative, like taking two derivatives of position, the instantaneous rate of change of your velocity. This is called acceleration. And so this is how physicists formally define position, velocity, and acceleration. And so there are established formulas for linear motion under the influence of gravity. And these are formulas that were discovered by Galileo. And you have this gravitational constant, which you call g, and it's roughly equal to, near the surface of the Earth, it's roughly equal to 9.8 meters per second squared. So meters per second squared. So position is like meters. Velocity is like meters over time. Every time you take a derivative, you're dividing by a unit of time. So derivative of velocity would be like meters over second squared. So the gravitational constant is a measure of acceleration. So the gravitational force is an accelerative force, at least as Isaac Newton conceived of it. Einstein kind of had other ideas in the early 20th century. Let's sort of save that for another day. If you're doing it in feet per second, it's like 32 feet per second squared. And so what were the formulas that Galileo and Newton deduced? And so what we deduce is that the acceleration is constant. The force of gravity is constant. And that's negative g. And this sign is by convention. It's just like because you want to eventually, you're thinking of like falling downward to the earth. So you're going to want a negative contribution that like brings you downward. The velocity. The velocity is like, I'm just checking the book so I can use the same notation that they do. The velocity was like the initial velocity that you started with minus t times the force of gravity. And your position was equal to what? It's going to be, we'll check their notation. It's going to be your initial position, which you call s naught, plus times your initial velocity, minus times squared over 2 times the force of gravity. And you can check this, like if you take the derivative of position, the constant, derivative constant will be 0. The derivative of t times initial velocity would be initial velocity. The derivative of t squared over 2 will be equal to t. You take the derivative of velocity, this will be 0 because it's a constant, and the derivative of negative g times t is equal to constant negative g. So these are formulas for linear motion that were just tested by experiment hundreds of years ago, and later on were put into a larger context. But it's your first introduction to this physics of linear motion and the relationship between them. One is the derivative of the other. You'll learn all about it in a physics class, that uses calculus. I'm not going to do tons and tons and tons of physics in this class. I don't think it's that, that important that we like privilege physics over other things in a calculus class. But I do want you to know that this is where calculus came from these kinds of investigations. And I have like an explicit example I can give you with some numbers, but I think we're close enough to the end that we may as well call it quits today. So learning objectives, what were we trying to get out of today's class? We're trying to help you understand physical interpretations of the instantaneous rate of change. That is to say, physical interpretations of the derivative. We saw an example with exploring rate of change as it relates to area of a circle. And we saw some examples with marginal cost in economics. And we saw some example with linear motion in physics. So that's all for today. Thank you, everybody, and we'll see you next time.